Hi everyone, welcome again to the course of structural biology. We are going through high resolution structural biology techniques, and now currently we are in the module of NMR spectroscopy. We have already discussed basic things about spectroscopy, basic application of NMR, basic principles of NMR. Today we will start with something which I talked about, which is chemical shift, which I also told you that have a very critical role in the technique of NMR spectroscopy. Today we will not study chemical shift, but we will understand what are the factors. Going through, I have discussed few, but now I have enlisted them so that you could see them together. So, chemical shift, as we know, in any given molecule, a given nucleus is surrounded by a cloud of electrons with specific density. You all know, like hydrogen 1 electron, carbon 6 electron. So, they differ. You will see here the electron. So, the nucleons have spin and the electrons have spin, and the electrons they are surrounded. So, they affect the spin of the nucleon. These electrons, we could say they are moving charges, exert a magnetic field. So, we told that because of the charge and spin present in the nucleon, they are behaving as a magnet. Electrons are also used as a magnet, exert a magnetic field at the nucleus, which is often opposite in direction compared to the main magnetic field, which is the magnetic field generated by the nucleons in the and aligned by the effect of the external magnetic field. Thus, the effective field felt by the nucleus is reduced from B0, which is the external magnetic field, by a factor which depends on the density of the electrons around the nucleus. So, if you have more electron, you have more effect. The precessional frequency is not same for all the nuclei in the molecule and depends on the electron density surrounding it, which means it depends on the chemical environment of the nucleus. As I told, a proton and a carbon, it would be different. So, what are the factors that affect the chemical shifts? One, hybridization state of carbon, sp3, sp2, sp. I have talked about hybridization, so you all know about them. Magnetic anisotropy, inductive effect, resonance effect, aromatic ring current effect, steric effect, and hydrogen bonding. They are the most common factor affecting the chemical shifts. Hybridization state of carbon. So, as I told, there are sp3 hybridization, there is sp2 hybridization. If you see, there is methane CH4 with 0.23 ppm and ethane CH3 0.86 ppm. When this sp3 hybridization goes to sp2 hybridization, CH2 double bond CH2, ethene, it goes to 5.28. So, it is a big jump. So, with the increase of S character, sp3 to sp2 is 25% S to 33% S. With the increase of S character from sp3 to sp2 to sp orbitals, the bonding electrons move closer to carbon and away from the protons, and because of that it causes desilting, and because of the desilting the chemical shift enhanced. Magnetic anisotropy, as we have discussed before, magnetic anisotropy arises due to the difference in shielding and desilting of atoms due to differential electron density in the molecule. The presence of a nearby pi bond or pi system greatly affects the chemical shift, that is called magnetic anisotropy. So, if you see, this is a double bonded carbon here, in both the top, above and below it is shielded, inside it is deshielded. Similarly, In a carbonyl, in the above and below it is shielded and in the side it is deshielded. Inductive effect. We are taking a group of compounds with CH3X, where X is replaced by different elements like CH3F when it is fluorine, CH3OH when it is oxygen, CH3Cl when it is chlorine, CH3Br when it is bromine, CH3I when it is iodine, CH4 when it is hydrogen, CH3 whole 4 Si when it is silicon. The electronegativity you see from fluorine it is 4.0, the most electronegative, oxygen 3.5, chlorine 3.1, bromine 2.8, iodine 2.5, hydrogen 2.1 and silicon 1.8. And the chemical shift is for fluorine highest electronegativity, highest chemical shift 4.26, for methanol in the presence of oxygen it is 3.4, CH3Cl it is 3.05, CH3Br it is 2.68, CH3I it is 2.16, CH4 0.23 and CH3 whole 4 Si it is 0, that is why it is used as a standard. The effect increases with greater numbers of electronegative atoms and their electronegativity. So, greater number of electronegative atom, what if you have chlorine in the presence of 3 chlorine which is CHCl3, the chemical shift delta is 7.27. By replacing one chlorine with one hydrogen it become 5.3, by replacing another chlorine with another hydrogen it become 3.05. So, with decreasing electronegativity containing atom the chemical shift decreases. Also the effect decreases with increasing distance, like CH3Br if the carbon and hydrogen the bromine is directly added it is 3.3, CH2Br where one carbon further it is 1.69, CH2Br it is 1.25. What we are talking about? We are talking about the hydrogen which is going further, like we are talking about only the red colored hydrogen. Otherwise, if you consider these and these, they are still closer, so they would have higher chemical shift in comparison to the red ones. Okay. So, with increasing distance from the electronegative atom, the chemical shift decreases. Resonance effect. So, we are having CH2 double bond CH2 with 5.29 ppm, all the protons are equivalent here and resonate at 5.29 ppm. Now, if you introduce a carbonyl group COCH3 keto group, actually you add this COCH3, the addition of a ketone group or keto group withdraws electron and decreases the shielding around the proton. So, it take the electron, so the shielding effect reduces, enhances the chemical shift. So, chemical shift from 5.29 now becomes 6.52. Then you introduce a OCH3. For OCH3, CH3 have the positive inductive effect and it puts the effect towards electron pushing. Because of electron pushing, the concentration of electron, the electron cloud would be enhanced. So, there would be more shielding. So, definitely there would be decreasing chemical shift which is happened. So, it reduces from 6.5 to now 3.93, or you could say from 5.29 to 3.93. So, the methoxy group will donate electron to the double bond and increases the electron density around protons, which results in enhancement in shielding. Aromatic ring current. So, you see the benzene ring external field is applied here, any nuclei above the plane of the ring is shielded. Now, there is circulating pi electron, here you see deshielding happen, which fills the shielding and deshielding comes together. Steric effect. Steric crowding around a carbon nucleus increases deshielding and moves resonances downfield. Like if you see carbon with 3 hydrogen, here it is a methyl, is methyl deshielded by 1 bond, then methylene deshielded by 2 bonds and methionine deshielded by 3 bonds. And you see that here the chemical shift actually change because of the steric effect. Hydrogen bonding, we have taken the example of methyl salicylate. In methyl salicylate, which has strong internal hydrogen bonding, you see the hydrogen bonding here, the NMR absorption of hydroxyl group is at about 14 ppm, way downfield. So, we have seen the different effects of factors on the chemical shift, and now we are coming to the point where we finished the last class, which is the coupling in NMR. So, if you look at, we have a compound which is CH3, you see CH3 CHCl2, see CH3 CHCl2. Now, the compound contains 2 type of hydrogens, it is very easy to understand, one type of hydrogen and a second type of hydrogen. So, how many peaks you are expecting? 2 type of peaks, and you see 2 type of peaks, right. So, the compound contain 2 type of hydrogen atoms. So, a doubly peak is observed at 2.1 ppm and a quartet is 5.9. So, up to now we discuss about peaks. We know 2 type of hydrogen, 2 peaks, but what are they? What are the splitting? Now, we will know about the splitting, why this splitting is happening. So, in the last class we have studied all the hydrogen NMR spectra, all had different types of protons that are seen as singlets in the spectra. Then we start discussing about the spectra of 1,1-dichloroethane. This is not the case like previous ones, spectra is seen in multiplets. So, we are going to more complex situation from singlet spectra of different hydrogens to multiplets. The appearance of multiple peaks are due to coupling with neighboring proton. So, now we are coming to a concept. What we know, if you start, we know that you need a nuclei with uneven spin, 1H C13, then we know the presence of electrons would differ, which is chemical shift, 1H and 13C would be different. Now, it is the third concept where we are talking about coupling. What is coupling? These 3 hydrogen would affect this, or on the other way this hydrogen will affect this. So, how it will happen? This is one hydrogen, if you remember, this would have 2 alignments, right, alpha state and beta state. These alpha state and beta states are affecting those hydrogens. So, how the peak will be differ? When you consider this one, the CH3, because there is one hydrogen, so it will create 2 states. So, there would be a doublet. Okay. So, delta equal to 2.1 ppm, integration of 3H agrees with the CH3 unit. Now, this one which is in 5.9, because of the presence of 2 chlorine will affect by them and have 4 peaks. We will discuss why, but this would have 1:3:3:1. So, we will come to explain that. So, what are the rules for spin-spin coupling? Chemically equivalent protons do not show spin-spin coupling. These and these are also neighbors, but they are equivalent carbons, so they are not showing spin-spin coupling. Only non-equivalent protons couple. So, this would couple with all of these 3. Protons on adjacent carbon normally used to couple. So, if they are 1 carbon apart, they are the best to do spin-spin coupling. Protons separated by 4 or more bonds will not couple. This is space, so the distance when it is around 4 bonds, so it is not going to couple, or better they are not going to show the effect. So, before going into this picture, I want to show you, this is methyl bromide, this is ethyl dichloride. Here you have 3 equivalent hydrogens, so they will have only 1 peak and would not split. Here you will have 2 type of hydrogen and this will have effect on them. So, they are getting doublet, whereas this will get a 4 peak, okay, tetraplet with 1:3:3:1. Now, coming to this, so HA and HB, if they are equivalent, they will not allow. So, it would go and couple only if they are different. HA can couple with HC, HA cannot couple with HD. So, spin-spin coupling, the interactions between the spin of neighboring nuclei in a molecule may cause the splitting of NMR spectrum. This is known as spin-spin coupling or splitting. The splitting pattern is related to the number of equivalent hydrogen atom at the nearby nuclei. So, we are taking the case of ethyl acetate, see CH3, CH2, O, CO, CH3. This is methyl ethyl acetate. Okay. The interactions between the spins of neighboring nuclei in a molecule may cause the splitting of NMR spectrum. This is known as spin-spin coupling or splitting. The splitting pattern is related to the number of equivalent hydrogen atom at the nearby nuclei. So, if you look at this one have no nearby. So, this methyl group will give 1 peak. These are having 2 of this hydrogen. So, they will give triplet. These are giving tetraplet. Let us see. Singlet, 3 equivalent position not coupled to any neighboring protons. Second one, this one, this will give 2 equivalent proton split 1:3:3:1. So, they have 3 neighbors. So, they will give quartet. 2 equivalent positions split 1:3:3:1 because coupled to the hydrogens of terminal methyl group having 3 identical hydrogens. This will give triplets, 3 equivalent protons. So, because they have 2 neighbors, so they will give triplet with 1:2:1 because coupled to the hydrogens of the CH2 group. So, coupling arises because the magnetic field of vicinal or adjacent proton influences the field that the proton experiences. To understand the implication of these, we should first consider the effect the CH group has on the adjacent CH3. The methine CH can adopt 2 alignment with respect to the applied field. As a result, the signal of the adjacent methyl CH3 is split in 2 lines of equal intensity, a doublet. So, we are talking about this, the CH3 CHCl2. Here, to understand the implication of this, we should first consider the CH3 group, that the CH group that has on adjacent CH3. The CH can adopt 2 alignments alpha beta with respect to the applied field. As a result, they will give a doublet. Okay. So, if you see external magnetic field B0 comes, the field are aligned which effectively disill the neighboring proton and resonance occur at higher frequency. On the other hand, fields are opposed. So, this is aligned. Field are opposed which effectively seals the neighboring protons and resonance occurs at lower frequency. Now, consider the effect of CH3 group has on the adjacent CH. So, if you see they are 3, so they have different combinations. As you see, they could have 1, 2, 3, 4, 5, 6, 7, 8 combinations. The methyl CH3 proton give rise to 8 possible combinations with respect to the applied field. However, some of the combination, that is why we have aligned them, are equivalent and there are 4 magnetically different effects. As a result, so you have 4 different effects. So, you have split them to 4 lines with 1:3:3:1. The proximity of n equivalent hydrogen on neighboring carbon atom causes signals to be split into n plus 1 lines. This is known as multiplicity or splitting or coupling pattern of each signal. So, we talk about splitting, now we are going to go for patterns. Equivalent protons or those with the same chemical shift do not show coupling to each other, very clear. If the neighbors are not all equivalent, more complex pattern arise. This is because of the difference in the values of the coupling constant. We have talked about when there are 3 hydrogen in a methyl group, it have 8 combinations. Now, among the 8 combination, we grouped them into 4, but if among these 3 hydrogen they are not equivalent, then that would be creating more complications. When looking at NMR, the most common coupling that are observed are those between hydrogen atom on neighboring carbon atom, vicinal coupling HACCHB, where 3 bonds are involved, that is the most common. To a first approximation, protons on adjacent sp3 carbon tend to behave as if they are equivalent. For example, the H NMR of 1 bromopropane. Now, we can do more a complete analysis including the application of the n plus 1 rule, which I am coming to 1,1 dichloroethane, where delta equal to 5.9 ppm quadrate, integration equal to 1 H desilted agrees with the CHCl2 unit next to a CH3 unit, n equal to 3. So, n plus 1 equal to 4 lines. Delta equal to 2.1 ppm doublet for the other one, the CH. For the CH Cl2 we would have, for this we will have quadrate, for this we have doublet. So, delta 2.1 doublet integration equal to 3H agrees with CH3 unit next to a CH. So, now coming to what is coupling constant. The distance between the peaks in a given multiplet is a measure of the splitting effect known as coupling constant. So, we talked about the split, how much they split you get from coupling constant, denoted by symbol J expressed in Hertz. Coupling constants are a measure of effectiveness of spin-spin coupling and very useful in analyzing proton NMR of complex structures. So, this is the coupling constant J. The coupling constant J, usually in frequency unit Hertz, is a measure of the interaction between a pair of protons. In a vicinal system of general type HACCHB, then the coupling of HA with HB, which is JAB, must be equal to the coupling of HB with HA, which is JBA. So, the rule is JAB equal to JBA. The implications are that the spacing between the lines in the coupling patterns are the same as can be seen in the coupling patterns from NMR spectra of 1,1 dichloroethane. So, because of this condition, if you see, the coupling pattern is same. So, so far we have emphasized vicinal coupling of hydrogen atom on adjacent sp3 carbon atoms. This coupling constant is typically about 6 to 8 Hertz. Coupling is controlled by geometry and the orbitals involved between the coupling nuclei. So, other types of system have slightly different coupling constant as compared to the CH3 carbon, which is 6 to 8. So, if you look at, as I told, alkane 6 to 8 Hertz, in double bond with cis 6 to 15 Hertz depending on the situation, trans 11 to 18 Hertz, geminal which is in between 0 to 5 Hertz, for aromatic rings ortho 7 to 10 Hertz, meta 2 to 3 Hertz, para 0 to 1 Hertz. So, this gives rise to the concept of long range coupling. Hydrogen atoms on a CH2 of a alkene do not have to be equivalent depending on what substituents are on the other hand of the alkene. As a result, they can couple to each other. This is a 2 bond coupling. Coupling between hydrogen atoms that are more than 3 bond is also possible, and that is called long range coupling. In general, the more bonds involved between the H that are coupling, the smaller or weaker the J value. Long range coupling is more common with rigid system, including the pi bond system of alkenes and substituted benzenes with delocalized pi electron. The presence of different coupling, different J values tends to lead to complex coupling. So, n plus 1 rule we talked about already. The multiplicity of signal is calculated by using n plus 1 rules. This is one of the rule to predict the splitting of proton signals. This is considered by the number of nearby hydrogen nuclei. If n equal to number of proton in nearby nuclei, 0 hydrogen atom has neighbor n plus 1 equal to 0 plus 1 equal to 1, which is called singlet. So, if the hydrogens are independent, have no coupling, then you get singlet. one hydrogen atom as neighbor putting effect is doublet, two hydrogen atom is triplet in that way. So, number of hydrogen atom present plus 1, and these would bring us to what is called Pascal's triangle. Pascal's triangle talks about what we talk the n plus 1, but it would talk about the intensity. So, n equal to 0 is singlet, n equal to 1 is doublet, where it is 1 is to 1, n equal to 2 is triplet 1 2 1, n equal to 3 is quartet 1 is to 3 is to 3 is to 1 in that way. So, individual resonances are split due to coupling with n equivalent adjacent protons, number of lines in coupling pattern L equal to n plus 1. The relative intensities of the lines in a coupling pattern is given by a binomial expansion, or more conveniently by Pascal's triangle. To derive Pascal's triangle, start the apex and generate each lower row by creating each number by adding the two numbers above and to either side in the row above together. So, what it means 1 1 1. So, this would be same if you go into that, 1 1 1 1 1 1 1 1 1 1, then you have 1 plus 1 is 2. Then you have 1 plus 2 is 3, 1 plus 2 is 3, then you have 1 plus 3 is 4 and 3 plus 3 is 6, 1 plus 3 is 4 in that way. So, for H NMR, a proton with 0 neighbors n equal to 0 appears as a single line, a proton with 1 neighbor n equal to 1 as 2 lines of equal intensity, a proton with 2 neighbors n equal to 2 as 3 lines of intensities 1 is to 2 is to 1. So, by coupling the concept of n plus 1 rule and Pascal's triangle, you could very well predict the number of lines you get, singlet, doublet, triplet, and their relative intensities. Coming to the interpretation of proton NMR spectra. So, CH3 CH2 Br, we have CH3, so CH3 CH2 Br. So, what you have CH3 CH2 Br. Okay. So, if you have that, you could easily understand that these are having 3 independent hydrogens. So, and so this is one category of hydrogen, they are one category. So, how many lines? 2 lines first, clear. These are methyl hydrogens. So, they would be around in between 1 and 2, right, close to. This is having chlorine, having desilting effect. So, they are higher. So, you know that there would be 2 lines, the first line is for methyl group, the second line is for the CH2 group. Now, this is giving them a quartet and this is giving them a triplet. So, the first one which is of methyl group would be a triplet and this would be a quartet. So, if you want to draw, you could draw. So, 2, so you have a ppm, you have this graph, right. You have, you know that you have one which is for methyl and you have one which is for CH2. Now, you know that because it is 3, it would be higher and this is lower, relatively lower. Now, you know that this one have 3 lines. 3 lines means 1 is to 2 is to 1. So, 1 half 2 1 and this one they would have a tetraplet, that would be 1 is to 3 is to 3 is to 1. So, 1 is to 1 is to 3 is to 3 is to 1. So, this would be your graph, and now you see exactly that you get. So, in that way now you could be able to interpret number of signals indicates how many different kind of photons are present. So, you get here 2. Position of signal indicates something about the chemical shift, the magnetic environment. Here you know that the CH3 carbon and CH2 carbon attached with chlorine is different. Relative intensity of signal I talked about, the first one 3, so higher, and second one 2, so relatively lower. Splitting of signals we discussed. What are the good solvent used in NMR? Solvent play critical role in NMR experiments. The following solvents are normally used in NMR experiment where hydrogen is replaced by deuterium: CCl4 carbon tetrachloride, CS2 carbon disulfide, CdCl3 deuteriochloroform, C6D6 hexa deuteriobenzene, D2O deuterium oxide. Now, coming to factors affecting NMR spectra, it is a kind of summary. Each different type of hydrogen gives a peak or group of peaks. So, you pick one, as I have already told here, you get one type of hydrogen and one type of hydrogen. So, two type of hydrogen, 2 peaks. The chemical shift, the delta in ppm gives a clue as to the type of hydrogen generating the peak. Like here, this is CH3 and this is with chlorine. So, this would be shifted like alkane, alkene, benzene, aldehyde, electronegative group, we know all of them and their effects. The integral gives the relative number of each type of hydrogen, 3 longer than 2, that is the integral we talked about. Spin splitting gives the number of hydrogen on the adjacent carbon n plus 1, for these 2 plus 1 3, for these 3 plus 1 4. The coupling constant J also gives information about the arrangement of the atoms involved, which is coming from the Pascal's law. NMR spectra of ethyl bromide. So, this is ethyl bromide. We already talked about ethyl bromide has 2 types of hydrogen. Now, you are understanding it more clearly. The downfield peak at about 3.5 ppm, which is for CH2 desilted by the bromine and appears as quartet due to the adjacent for methyl group. The upfield peak at about 1.7 ppm is the CH3 and appears as triplet due to the adjacent methylene. Coming to the NMR spectra of propyl bromide. So, we have CH3, CH2, CH2, Br. So, here the first one with bromine, one type of hydrogen, second one in between have second type of hydrogen and 3 type. So, 3 type and 3 spectra. The middle CH2 at about 2 ppm seems to appear as a hextate 6 line due to the total of 5 neighbors, 3 plus 2 5 neighbors. So, this is due to an important approximation that helps simplify the spectra. The approximation allows us to assume that the CH3, which is the methyl group, and the other CH2 are similar neighbors, and that the coupling constant involved are the same, which is not actually. So, the coupling constant of the middle CH2 to each of the other groups is essentially the same, that is what we are considering. This is reasonable expectation because both the other groups are sp3 carbon system and there is free rotation of the chain. If this approximation does not hold or apply, then more complex coupling patterns are observed. So, it is interesting, if you see here we are considering CH3 CH2 as like this CH3 and this CH2 having same effect on this, which is not exactly true, but they are close because both of them are sp3 equidistant and not very different. But if you do not consider that, then the spectra would be more complicated. So, we have seen in this class the effect of different factors on chemical shift. We talk about spin coupling constant and their effect and how they make n+1 rule and Pascal's triangle. Now, we will shift to C-NMR spectroscopy. It is useful to compare and contrast H-NMR and C-NMR as there are certain differences and similarities. 13C has only about 1.1% natural abundance. We have talked before, the main isotope is 12C, 13C, but 12C is not NMR active. So, 12C does not exhibit NMR behavior I equal to 0, 13C nucleus is also a spin half nucleus like a proton, 13C nucleus is about 400 times, some people say more, less sensitive than hydrogen or proton nucleus to the NMR phenomena. Due to the low abundance, we do not usually see 13C coupling like 1H coupling. Chemical shift range is normally 0 to 220 ppm in the higher range. Chemical shifts are also measured with respect to tetramethylsilane CH3 whole 4 Si TMS, which the standard is also used as standard in proton NMR. So, it is good, we could use this standard in both the experiments. Similar factors affect the chemical shifts in 13C as we have already seen and discussed for H-NMR. Long relaxation times, excited state to ground state means no integration. Normal 13C spectra are broadband proton decoupled, so the peaks show as single lines. Number of peaks indicates the number of type of carbon. The general implications of these points are that 13C NMR spectra take longer to acquire than H-NMR, though they tend to look simpler than the proton NMR. Accidental overlap of peaks is much less common because less intensity and all than for H-NMR, which makes it easier to determine how many type of carbons are present. What does broadband proton decoupled mean? The resonances due to 13C nuclei are split by neighboring hydrogen atoms. This splitting would complicate the appearance of the spectra, making them harder to interpret. Therefore, in a normal 13C spectra, these couplings are removed by applying a continuous second radio frequency signal of a broad frequency range that excite all the proton nuclei and cancel out the coupling patterns due to the interaction of the proton with the 13C. So, when it is proton, you have to understand there are number of protons and they are different in their chemical nature. So, identifying each of them is important. But if you do the same with carbon, then it becomes very complicated, and that is why this decoupling happened. Now, each carbon is seen as a single line. Of course, information is being lost by doing this, such as how many hydrogens are attached to each carbon, and that is why we need 2D NMR, which I will talk about little. In off resonance decoupling, the one bond CH couplings are retained. So, the signal for a particular carbon is given by the number of attached hydrogen in accord with n+1 rule. So, for example, a CH3 shows as a quartet and a CH2 as a triplet, and that gives us the information how many hydrogens are attached there. 13C chemical shifts, we discussed about 1H. The most significant factor affecting the chemical shifts are electronegativity of the groups attached to the carbon, Hybridization of carbon, a simple correlation table of 13C chemical shift, which you could see here. You will see that when you have carbon carbon saturated single bond, these have lower values. So, this is 0 to 220 ppm. When you see carbon is attached with electronegative, then it enhance, carbon is triple bond, it enhance, then carbon with double bond, more enhance, aromatic, more enhance, carbonyls have the highest. So, single saturated bonds have values in lower side, carbonyl and modified carbonyls have values in higher side. So, 0 to 220 they are categorized in this way as you are looking at. Interpreting carbon NMR spectra. The following information is to be gained from a typical broadband decoupled 13C NMR spectrum. How many types of carbon indicated by how many signals there in the spectra. So, how many lines, that many carbon. What type of carbon indicated by the chemical shift of each signal. So, it is similar nature. Let us take a look. So, carbon NMR spectra of ethyl ethanoate, CH3, CO, O, CH2, CH3. How many carbon? 4 carbon. How many peak? 4 peak. Okay. Ethyl ethanoate have 4 type of carbons. We could easily see here. If you see 1 type, 2 type, 3 type, 4 type. Carbonyl carbon, this one, methylene carbon and 2 methyl carbon connected to different position. So, 4 peaks are observed. Ester carbonyl peak is at 171 because it is carbonyl carbon, we talked about this. Desilted CH2 group at 60 ppm and 2 methyl carbons are at 16 and 20. Now, a benzene ring with of acetophenone, you will see that here acetophenone has 6 type of carbon. So, 1 type, 2 type and then connected types. How far there? Carbonyl carbon easy, methylene methyl carbons, aromatic carbon directly linked with acetyl group, aromatic carbons ortho, meta and para. So, 1, 2, 3 easy, then ortho, meta, para 6. So, 1 carbon, 2 carbon, 3 carbon, then ortho, meta and para. So, how many carbon? 6 carbon. So, 6 peaks are observed. 4 types of aromatic carbons having peaks between 125 to 140, as we have already discussed that. Ketocarbonyl at 198 ppm and methyl carbon at 27 ppm. And 1D NMR spectrum contains the following information for analysis: chemical shifts we have discussed in details, spin spin coupling we have discussed that too, intensity, the number of hydrogen. All this information are used to deduce the structure of the molecule. Many times it is not possible to assign all the chemical shift if the spectrum is complex. And when I say complex, I want to tell you that for discussing the details of the basics so that you can get the basic knowledge, still now we are discussing about small molecules, but our journey is to protein, because this course is structural biology of macromolecules. Hence, only the region of interest is analyzed. For example, if a substitution reaction on a benzene ring is to be checked on the aromatic region, need to be analyzed. Also, that leads to develop multi-dimensional spectra. So, we have discussed about different effects, how that give a NMR technique, how that affect the proton, how that affect the carbon, what we are getting from 1D hydrogen spectra or proton spectra, what we get from 1D carbon spectra. Now, we are shifting to 2D NMR spectra. So far the NMR spectral methods we have discussed have been one dimensional, since they have a single chemical shift into the coordinate axis. With the development of more advanced spectroscopic methods, as computational power has increased, it has become possible to obtain two-dimensional spectra. In two-dimensional experiments, both the x and the y axis of chemical shift scales and the 2D spectra are plotted as a grid like a map. Information is obtained from the spectra by looking at the peaks in the grid and matching them to the x and y axis. So, the basis of 2D NMR is interaction of nuclear spins, 1H with 1H, 1H with 13C, etc., and not with 13C with 13C, right. You have to remember 13C is no, plotted in 2 dimension. Normal spectra 1D NMR are plots of intensity versus frequency. In 2D NMR, intensity is plotted as a function of two frequencies called F1 and F2. In general, 2D NMR is divided into two types: homonuclear, heteronuclear. Each type could provide through bond, which is quasi type, through space, noisy type coupling information. So, 4 periods in 2D experiment: first the preparation, then evolution, then mixing, and then detection. Preparation, which means spin system relaxes and then excited by the radio frequency. Evolution, T1 chemical shifts and spin coupling evolve. This is the time domain which is incremented during the 2D experiment, was not there in 1D. Mixing, radio frequency pulses are applied and create observable transverse magnetization, and detection, T2 observable transverse magnetization is recorded, it is usually labeled with T2. So, in 2D NMR spectra we have two frequency axes, often symmetrical about the diagonal, correlates peaks in 1D NMR spectra plotted on the sides. If you see one side 1D, another side 1D, means 2D. Diagonal peaks, if you see the diagonal peaks, they are same. So, if you see these with these, so they are symmetry related. So, same as 1D NMR spectrum. Cross peaks connect different peaks in 1D NMR spectrum that are interesting, arise from scalar coupling or other magnetization transfer mechanism. So, these will give us more information in the 2D spectra. So, correlation between two chemical shifts, how we see that. So, the compound is CH3, CH3, CO, CH3. So, CH3 connected to a carbon. So, CH3, CH, CH3, CO, CH3. If you look at that, you will see that there are 3 types of hydrogen, because they are equivalent, they are, this is one. So, these 6 are equivalent, they are connected to one carbon and all. This is another one and this is another one. So, these two they have effect of 1. So, they are doublet, this is single, so singlet, and this one have 6. So, this is septet, that is one, and carbon have 4 peaks. So, 3 peaks in proton spectrum, as we have discussed 3 peaks, and 4 peaks in 13C spectrum. So, if you look at, there would be 3 into 4, 12 combination of pairing proton with its C13 peak. Which pairs are correct? Now, based on the peak position and coupling, yes, you could talk about the correct pairing, but is there a direct way to get the correct 1H to 13C interaction pairing? So, if you look at, for proton A, B, C, it have 3 peaks 2.5 ppm, B is 2 ppm and C is 1 ppm. Carbon's 3 peak which is combining is 40 ppm, 25 ppm and 18 ppm. So, this is an example of correlating to heteronuclei, because we are combining 1 H with 13 C, right. The 2D spectrum is said to correlate the frequency, and you get 3 points where A you know with X, B with Y and C with Z. In the carbonyl carbon there is no hydrogen, so you do not get any interaction naturally. And if you see here, you have in one axis you put the proton, in other axis you put the carbon. Now, if you have this proton, which protons are coupled to other proton? For getting the coupling, 1D NMR would not be good enough, but when you plot 1 H versus 1 H, you get which are coupled to each other. C and A you will get coupled. So, this is an example of correlating to homonuclei, because you are doing the coupling between one proton with another proton. B is not coupled to any 1 H, hence it is absent in the spectrum, it is not coupling with anyone. Like C, you see the 4th spectra of carbon was not present in the other one, here the this is absent. So, you get how they are coupled here. So, coming to routine 2D NMR experiments, there are majorly 3 type of NMR experiments: homonuclear through bond correlation method. So, homonuclear through bond correlation method is, as we have seen, the bonded interactions between one proton with another proton, that is homonuclear through bond correlation method, that could be studied. Heteronuclear through bond correlation method, carbon and hydrogen heteronuclear, and through space. So, it could be homonuclear through space correlation method or heteronuclear through space correlation method. So, basically we have 4 type of routine 2D NMR experiments. So, when you look at homonuclear through bond correlation method, there is correlation spectroscopy or COSY, exclusive correlation spectroscopy or ECOSY, total correlation spectroscopy or TOXY, incredible natural abundance double quantum transfer experiment or inadequate. Now, heteronuclear through bond correlation methods are heteronuclear single quantum correlation spectroscopy or HSQC, heteronuclear multiple quantum correlation spectroscopy or HMQC, heteronuclear multiple bond correlation spectroscopy or HMBC. Through space correlation methods, nuclear over Hauser effect spectroscopy or noisy, rotating frame nuclear over Hauser effect spectroscopy or noisy, heteronuclear over Hauser effect spectroscopy or hazy. So, in the next class we will discuss about that, all the routine 2D NMR experiments, how they converted into 3D NMR experiments, and most importantly how 3D NMR experiment help us studying protein. So, in this class today we had gone through several topics, starting from the factor affecting chemical shift to spin coupling constants, the NMR spectra of one proton and its effect of all of these things, carbon spectra, how carbon 113C carbon is affected, how they are coming together, what are the factors they are affected with, and how they look like. Then we come to concept of 2D NMR, how or why 2D NMR spectra is required, how they are interacting, what type of 2D NMR spectra are there. In the next class we will continue with the details of at least brief details of all those methods. Thank you very much.